Good evening to
And
our
I'm audible, right?
yes, yes.
Okay. So, okay, let's start with the webinar. So, hi everyone. Uh, Firstly, thank you to the IET S.P.I.T committee for inviting me for this webinar. I'm going to talk about what in general embedded systems are and delve deeper into one of the embedded systems, which is the Arduino board. Actually, can I? So, someone's not muted. I would request everyone to please mute. Thank you. So yeah, let me first introduce myself. I'm Karan Magia. I'm an alumni of S.P.I.T. I graduated in the year of 2014, post which I did my master's in the field of computer engineering from University of Florida. And after that, I went on to work for Intel for 3 years. I worked in the data center chip design team. We worked on the firmware that booted the chip to a good state, and then the software can then use the chip. Post that, I switched companies, started working for Nvidia. I've been working for Nvidia now for last 2.5 years almost. Earlier, I used to work for the Nvidia's Boston office, and then now I moved to India permanently, and now I work from the Pune office of Nvidia. So that's all about myself. Let's see what do we have for today. So the agenda of the webinar is first, actually, yeah, first I'm going to talk about what embedded systems are in general. Uh, we'll try to see what does a normal embedded system look like, how do the components of the embedded system look like, what are the applications they are used for, and why anyone would prefer an embedded system over a general purpose system. Next, I would move on to Arduino, give a brief intro about what the Arduino platform is, why is it so popular, and how one can use it for their own benefit. Next, we'll look at the Arduino Uno board's hardware. How does the hardware look? What all components are present on the board? And then move on to discuss more about the IDE. IDE is basically the software that you would use to program the Arduino board. And lastly, I would also talk about the other embedded boards that are out there in the market, and you guys can use it for your projects or prototyping. Post which, I will leave the floor open for any questions if there are any. But yeah, feel free to ask any questions in between too. I would want this session to be as interactive as possible. Uh, yeah. So without wasting time, let's just start with uh, what are embedded systems in general. So embedded systems are minimalistic systems which are designed to do a particular or a dedicated task. They are supposed to be designed in a way that they are inexpensive and they just do the task for which they are designed. So there are too many options in the embedded systems industry out there. You have Arduino, you have BeagleBone, you have Raspberry Pi, you have lot many of there, but most of them in general look like very similar. So they have few basic components on the system, and that's how the board drives the task it is supposed to do. So few of the components on any of the embedded system are it will have the brain of the system, which is the microcontroller or the microprocessor. This microcontroller or microprocessor will drive all the other peripherals, take input data from the sensors, compute it, make decisions based on it. So every embedded system will have a microcontroller or microprocessor, and the processor will be selected based on the application the embedded system is built for. Next is the firmware. Firmware is basically the code that you will write for the system. So you'll write this firmware code, which will do a dedicated task, and then you load that firmware onto the board, which will run on this microcontroller or a microprocessor, which will execute the task. So that's what the firmware is. Next is the memories. So for your firmware to be there on the board, you will need some kind of memory on the system. It can be a flash memory, it can be an EEPROM, it can be a SRAM, or it can be some other type of memory which is there on the system, where you load your code and your microcontroller will pick up the code from there and execute it. Next is IO pins. So basically, whenever you want to do a particular task, your microcontroller or processor will compute the data and would make certain decisions. And to take those actions, it will use those IO pins to connect to the external world and drive, let's say, an LED or a motor or some sort of sensor. So those sensors or the external peripherals are connected to via these IO pins. Next is every system needs to have a VR. VR is basically a voltage regulator. So every board will be given a power source, but that power source may not be that stable. It will not be regulated. So you will always have a voltage regulator on the board, which is extremely important because all of your components need a stable, regulated power source. So your VR is going to provide that regulated voltage source. Next is you have the COM ports. So your system standalone can compute data, but it would need to talk to the external agents or the external peripherals or systems out there to take certain actions. So you have various kind of communication ports on the embedded system and the connected system. So it can be a UART system, it can be a USB based system, it can be based on different protocols out there which are used for communication. Last but not the least, there could be other peripherals. So other peripherals meaning based on the application, you'll have devices connected to the embedded system. It can be so if it's a drone, it can have a camera connected to it. It can have uh, it can have a proximity sensor connected to it. It can have basically different sensors connected to it. Those are basically the peripherals which are connected to the board and which will be driven by the microcontroller or the processor on the system. So basically, what does an embedded system comprise of? It's basically all these basic components that work in tandem to provide your system, which will execute the dedicated task at your hand. So yeah, these are the general components, but they may vary based on what your application is for this system. Next, where are these systems used? These systems are used from something very basic like a system which is used to count your pulses, something like an oximeter, to something as fancy as a drone with tens of sensors and camera modules on it. So there are applications in the medical field. Basically, every medical device which is supposed to be somewhat smart will have an embedded system running at the heart of the medical device, which will not just compute the data. It will take input, uh, compute the data, and present it on some sort of LCD or some sort of display device. Next, you have defense. The defense industry is a very, very big customer of the embedded systems market. So, defense industry, every defense equipment is becoming smarter day by day, and they need to make such smart decisions, and they need an embedded systems at the heart of it again to drive all these functions. Next is the consumer device market, IoT or appliances, basically. So there's a new push for every device at your home to be smart, to be able to talk to you, and to be able to recognize things, to be able to capture images and deduce things out of the images. So every such IoT device or appliances at your home, or drones or robots, as they are becoming smarter, they need better and more powerful systems at the heart of it. And again, these appliances can be really small and they can do a couple of tasks, but it can be as complex as a full-fledged robot, which can understand human speech too. So basically, there are too many applications for for a system. So based on your application, you'll decide the system which works well for your purpose. So so there are ample of applications, and we talked about what embedded system is. But we also have a very generic system, right? We have a laptop which can pretty much do everything what an embedded system can do. It can capture image. It has a camera module attached to it. You have USB ports through which you can connect devices to it. Uh, so why would someone use an embedded system instead of a full-fledged system like a laptop or a data center or a PC at your home, right? So the reason one would use an embedded system is, firstly, an embedded system is supposed to be low power. This is a relative term in the sense that it will just consume power for the task you are building this embedded system for. Uh, for an example, consider that you're deploying a system in a remote area where the system is supposed to capture data intermittently and then transfer this data via via some communication protocol to the larger data center system, which will then use this data. But the data that is capturing this, but the system that is capturing this data, right? It needs to maybe it is deployed in a remote system where human access is barely possible. So you would want the system to work as long as possible without any human interference, right? So that's why you would want the embedded system to consume as lesser power as possible and work as long as possible. So one of the key characteristics of an embedded system is they are supposed to be really low power. Next is the embedded systems are really inexpensive. So if you think of an Arduino board, it costs around $15, depending on which board you select, but it will cost around $15 to $30 for the entire board with the microcontroller and the components on it. But if you compare it with just the processor chip on your laptop, just the chip, it will cost you more than 100 or $150. So so an embedded system is supposed to be really inexpensive, and that's how you can scale the usage of the system and deploy it at every corner, which will then be used to collect data. Next is an embedded system provides a better security story. This is becoming really important because as we are advancing with more and more systems around us, security is becoming a really important aspect of a system. You don't want attackers or hackers hacking into your system and manipulating data, right? Imagine the embedded system is a medical device, and if a hacker or an attacker tries to manipulate the data or tries to even kill the system, right? Even denial of service of such systems will be really detrimental for the hospital or the unit there, right? So the minimalistic design or lesser connected peripherals, the lesser connected the device or the system is to the rest of the infrastructure, the lesser possibilities of it being hacked and used for any malign purposes. So it provides a better security story that way. Next is a guaranteed response system. So you see that even if you consider your laptop, right? Your laptop crashes a lot, it hangs a lot. So let's say if you have deployed a system which is a very mission critical system and which is very time bound, you don't want your system to respond. You don't want your response of the system to be uncertain, right? You would want the system to provide your data at the required intervals at the right time. So an embedded system does that because it runs a very simplified software. For example, the Arduino board, it runs just a small piece of firmware which just which just does one small dedicated task, and there are very lesser chances of the system being crashed or if this for the system to hang because there's not much complexity in the software there too. So and also the more software you have, the more possibilities of bugs to be there in the software and the more possibilities of the system to crash. So yeah, so an embedded system with minimalistic design again provides sort of a guaranteed response, which is really important in mission critical uh, applications. So these are basic characteristics of an embedded system. Because of these characteristics, one would prefer using an embedded system or an ASIC system which does a particular task. ASIC is basically application specific integrated circuit, right? So this circuit or this system does a very specific task and provides the required output at regular intervals whenever expected. So um, yeah, so I would want to pause here and see if anyone has any questions. If not, I'll just move on. Okay, moving on. So that's what an embedded system is, right? We discussed what components there are on the system, the applications, and why one would prefer an embedded system. Now let's look at one of the most popular embedded boards used for simplistic design, for the reasons of simplistic design and the options available in this platform, right? The Arduino system. So, firstly, just a brief about the Arduino system. Arduino platform is developed by this company. Arduino is the company itself. It is a Atmega microcontroller based system. So, like every embedded system has a brain chip on the system, uh, like the microcontroller here, right, or the microprocessor. The Arduino board has a Atmega microcontroller at the heart of it, and this is the microcontroller that drives the entire system, that makes decision based on the input and drives the output signals. So Arduino is a minimalistic Atmega microcontroller based system. It is a low power system in the sense it just consumes around 200 to 300 milliwatts of power. Uh, so you could just combine the system with a small battery and deploy it for days to work without any interference. So it is a low power system. It is really inexpensive, uh, meaning you could buy a Arduino board for around $15 or so. So compared to any of the other general purpose system or any other embedded system, Arduino board is a very inexpensive option you have. The next is it has high IO current drive. What this means is you can connect a high current LED or a servo motor or any kind of motor that requires high IO current, uh, and you wouldn't need an external power source. The Arduino board itself can drive these peripherals without any issues. So these are some basic characteristics of the Arduino board. Um, uh, and because of these, they are like widely used for uh, college projects or even prototypes in the industry. Next is the Arduino company. They provide different flavors of the same board, meaning there'll be an Atmega chip at the heart of every board, but then there could be different modules connected to the system. For example, there's an option with a board which has a Wi-Fi module on it, so that you can actually create a system which can transfer or receive data via the Wi-Fi, or you could even have a Bluetooth module on it. So there are different flavors of the same board. So based on your application, you can decide which particular board you would want to select. Uh, Next is Arduino board is very widely used for prototyping. So let's say you have an amazing idea of an embedded system, and you're trying to create a product out of it. The first thing you will do is prototype the product and see if it works and if it functions as per your expectations, right? So that is what prototyping means. And Arduino board is very widely used for prototyping basic applications. And once the creators prove that the system that they have designed, or the code or the firmware that they have designed, works and provides the expected output, they create the actual system, the actual final product, which can be sold to the which can be then sold to the consumers. So the Arduino systems are also used used directly in the consumer market, but they are widely used for prototyping. Next is the Arduino IDE. So there are few of the hardware. So Arduino platforms provides two main things: the hardware board, which you can use, which has the microcontroller and which drives the entire system, and there's the IDE. IDE is basically the integrated development environment, basically a tool which you can use to write your program, which will flash on the Arduino board, and you can have the entire system available. So the Atmega microcontroller based system, all these low power, inexpensive, high IO current drive, these are the hardware characteristics of Arduino. There are different flavors available, and then the Arduino company also provides the Arduino IDE, which is again available on their website. One can just download the tool and just start designing their firmware. So this was just an intro. We will now we'll now look more into the Arduino Uno board. So as I mentioned, there are different types of Arduino boards available. You would need to select the Arduino board that you want and that serves the purpose of your application. But just to get started with, I'll talk about the Arduino Uno board, which is a basic board which one can get started with and learn more things about the platform. So so this is how the Arduino board looks like, uh, with all the components on it. You see that you have different type of boards, right? You can even solder the components on the board, but on this board, all of the components are surface mounted, meaning all of them are SMDs, and hence you have a very very tight connection on the entire PCB. So this is how the Arduino PCB looks like, with all its Arduino Uno board's PCB looks like, and with all its components around it. So I'm going to briefly talk about a few of the important components here. So this uh, this is the brain of the Arduino system. It is the Atmega 328P microcontroller. It is the brain because it takes the input, does all the computation, and drives the output. It is the it decide it makes it decides the actions that the system needs to make based on the input. Uh, we'll talk more about the Atmega 328P in the coming slides. Next is we have these analog input pins. So you could connect different sensors, analog sensors to it. Get the input from here. The board will pass the inputs to the microcontroller, and based on the inputs, the microcontroller will then make decisions and drive the output peripherals connected to it. So there are 6 analog input pins on the board. Next is you have the voltage, ground, 5 volt, 3.3 volt, and the reset pin. These pins are basically used to control the board or even get an output of 5 volts or 3.3 volts. You can use these based on your application again. If you want to connect an external device with a 5 volt source, you can use these pins, or 3.3 volt source, you can use this pin, for example. Next is the DC jack. This DC jack is basically the point where you connect the adapter to the board. So this Arduino board requires power to run, right? So like you charge your phone, this is a and your phone has a connector to it, charging connector, right? So similarly, this is the DC jack on the board. There's no battery on the board, so you would need to provide a continuous power for its operation. So this is the DC jack. You can connect a 5 to 10 volt adapter and provide power source to it. Now this silver box here is the USB Type B connector. So this can be used for 2 purposes. One, you can design your firmware on your PC or laptop, and when you want to flash the firmware on the board, you would need this connect. You would need to connect the USB cable to this connector, and then you can flash the firmware using the ID on the board. So that is one use of this connector to flash the firmware, and the second use is you can also use this for you can also use this as a power source to the board. So let's say if you don't have the adapter, you can use the USB connected to the PC, which will drive the board. Next is this red button. This red button is basically the reset button. Whenever you press this button, the entire board will reset, and the Atmega 328P will start executing from the first line of code. So next is these digital I/O pins. These pins are used to provide a digital input or output. You can connect devices like LED, servo motors, other sensors like proximity sensors, all those to drive them. You can use these pins to provide input to those devices or sensors. These are also some of the pins are also multi-purpose in the sense that there's a TX and RX pin. We will look at these 2 pins later on too in the coming slides. But just to give you a brief idea about what this is, the Atmega microcontroller supports a serial communication channel, basically a UART channel, right? So basically, UART is a serial communication protocol. So you would need 2 pins, mainly a TX pin and an RX pin. RX is to receive data, TX is to transfer data. So you can write your program in such a way that you can use this TX and RX pins to communicate to other device which also supports the UART protocol. Next is there are few LEDs there are few LEDs on the board which help you debug any issues if there are any, right? So for example, this LED which is connected to the digital pin 13, you can use this LED for any of the any basic um function of the board. Meaning, you can make this digital pin 13 as an output pin, and you can just drive the pin high or low, and based on that, the LED is connected to the pin 13, and the LED will be turned on or turned off based on whatever you write to this pin 13. So this is just a way to check that your code is working fine on the system. Next is this LED, and this LED will be turned on whenever the board is provided a power source. So this is the basic step to debug any issue. So if this LED is turned on, that means that your board has at least powered up. If there are any further issues, that means it's mostly with the code that you have written, and that's running on the Atmega. But if this LED does not turn on, that means the board there's a loose connection on the board, or the board is not receiving a good power source. Then there are these two TX and RX LEDs. These help us indicate whether we're able to transfer or receive data or not. So these are connected to these TX and RX pins. Whenever we are using the UART protocol and whenever we are transferring data, the TX and RX LEDs will turn on and off. Uh, so this is about the entire board. Now let's think about how would one flash any kind of software onto the Atmega controller, right? So the PC or the laptop that you're using to design the code supports USB protocol. The board supports a UART protocol. The UART protocol is different than USB protocol, so you would need a bridge or a connector between these two protocols so that they can communicate with each other, right? You would want the PC to communicate to the board so that you can flash the code on the board, right? So there is this Atmega 16U. This is another small microcontroller, and the sole purpose of this microcontroller on the board is to convert the USB packets that you receive and convert it into a UART based packet, which the onboard Atmega 328P microcontroller can understand. So this is like just a bridge between your PC and the Atmega controller, main Atmega controller. So it will just convert the USB packets to the UART packets. Uh, so this is how the entire board looks like. Next, we'll look at the Atmega 328P microcontroller in detail. Like we'll talk about a few characteristics of the microcontroller. So most likely you guys are in your engineering, right? In your second year or third year of engineering. So you might be studying, you might be having courses on microprocessors. You might be studying the 8085 or 8051. So similar to those microcontrollers or processors is Atmega 328P. This is the pin diagram of the Atmega microcontroller. It is a DIP package, meaning there are two parallel lines with pins. DIP stands for dual inline package, meaning there are two lines of pins on the chip. Each pin has multiple purposes. It can be used as interrupts, or it can be just used as a data pin. It can also be used as uh, transmitter or receiver channel. Um, it can be used as ADC. ADC is basically analog to digital converter pins. So there are multiple purposes for the same pins on the chip, and this is done so that you can then so the chip can support multiple functionalities using limited set of pins. So this microcontroller is a 8-bit microcontroller, and what that means is the internal registers on the microcontroller, or the data bus on the microcontroller is of 8 bits, 8 bits wide. You'll hear more about it in your 808 8085 or 8051 courses, where they talk about 8085 being a 8-bit microprocessor, or 8051 being a 8-bit microcontroller. So the internal registers of this microcontroller are of 8 bits wide, basically. Then this microcontroller. So before we go to the memory section, just want to highlight the fact that microcontrollers and microprocessors, they have a common function. Is basically to do some computation and drive the output. But there are differences between microprocessor and microcontroller. So uh, a microprocessor is just the compute unit. It's basically the central processing unit, which does the computation and then delegates the task of storing data or transferring data to other peripherals on the board. But a microcontroller, along with computing the data and making decisions, it also has on chip memories. It also has the on chip I/O devices, which we can use. So this Atmega 328 has three type of memories. There's a flash memory, right? This flash memory is a non-volatile memory. A non-volatile memory is which retains the data after every power cycle. So this flash memory is used to store the firmware code that you have designed. So whenever you flash the firmware code, that program or your firmware is residing in this flash memory. And this is non-volatile, so that every time you reset your board or every time you remove the power and reapply the power source to the board, the code is still there on the chip, and you don't need to flash the code again and again. So this is the flash memory. Its size is 32 KB. That means your firmware size or the firmware code that you're writing cannot be more than 32 KB. Next is the SRAM. This SRAM is basically an internal memory used by the microcontroller for its internal purposes. Meaning, let's say that the microcontroller is taking inputs. Based on the input, it is going to compute some data, right? So while computing this data, it may need to store some intermediate output values, right? So the SRAM is basically used for execution of the Atmega microcontroller for the processing of input. The next is there's EEPROM. EEPROM is basically again a non-volatile type of memory, which means you can store some data on the memory, which will and this data will be retained through multiple power cycles. So let's say that your embed system has computed some data, and it needs to store that data forever, even even when the power source is not connected to the system. The microcontroller can store that part of the data to this EEPROM. Again, the size of the EEPROM is just 1 KB, so you cannot store more than 1 KB of data. Um, so yeah, and lastly, there are timers and counters on the microcontroller. So for example, if you want to do a particular task in some intermittently after a regular time interval, you would use these timer and counter modules to add delays to your code, or just spin till the time the timer expires, and then you would repeat the task again. So just to sum up, the Atmega 328P is an 8-bit microcontroller with on-chip memory. It is a 28-pin DIP package. It has and counter modules on it. So it is basically a system. Uh, it also has multi-purpose pins, which can be used for communicating with other devices, or just as input-output devices, or ADC input-output devices too. So this is the brain of the embedded Arduino Uno board, the Atmega 328P. So uh, we looked at the Arduino board. We looked at the Atmega chip. The next thing is to look at the Arduino IDE. So we looked at the Arduino hardware part of it. That's basically the board and the components. The next thing is to is to see how one can write their own code and then flash it onto the system. So the good part is the Arduino company, they provide a really simple software that anyone can use and write their code and flash it onto the system. So this is the website of the Arduino company. They have this is the software section, the documentation for the software section. So they have this Arduino desktop IDE. This IDE is basically like any other code editor or code compiler. You can download these IDE software from the website, and then you can use it to write your own code. And then it will also help you flash the code onto the Arduino Uno board system. So that is one way how one can design the code and flash it onto the system. The other way is this web editor tool, and I really like this web editor tool because it gives you the flexibility to move across different systems and still have your code online where you can just pull the code and flash it onto the system. So the IDE and the web editor work almost the same way, meaning you can use it to design the code and then it will help you flash it onto the system. So just for simplicity, I'm going to talk more about the web editor, but just keep in mind that the IDE is exactly similar, and they have already mentioned the steps on the website about how one can go and install the software on your system and start using it. So, as I was saying, we'll look at the web editor. This is how the web editor of the Arduino platform looks like, right? This is just like any other website. You can log into the website. You can have an account so that it retains your codes or the firmware or the code design that you're working on. So it has a cloud running behind it, which saves all your data. So you can use this web editor, port your code across multiple systems, and still work flexibly. So this web editor, to get started with this web editor, the first thing is you select the board that you're using. So for our demonstration purpose, I'm using this Arduino Uno board. But if you see, there are lot many options here. You can just select the board that you're using, and based on the board that you're using, the web editor tool will load all the libraries that you can use in your code. So I've selected Arduino Uno here because we are talking about the Uno board. And this cross sign here indicates that there's no board connected to the laptop right now. I don't have the Arduino board physically available with me. But whenever you connect the board and provide a power source to it, you'll see that this cross sign will disappear, and that means that the Arduino Uno board is connected to your system, and your editor was able to recognize it. If in case you're not able to recognize the Arduino Uno board on your system, there are steps mentioned on the website about how you can go and debug it. It's basically that you need to check all the ports on your laptop, and you just need to provide some permissions for the Arduino board to access the ports on your laptop, and vice versa too. So it is a very simple process. You can just connect the board, and you just need to. It will prompt you to install a driver, and then you're all set to start designing the program and flashing on the board. So the first step is to select the board. Next step is to write your program. So now we'll look at some basic program, uh, and for this, I'm going to start with this bare minimum code. So your firmware design for the Arduino is very simple. It has two parts to it. First is the initialization part, and second is the task. The initialization part is the part where you decide the functions of the pins or the functions of the analog or digital pins or the UART module on the board. So as I mentioned that there are different IO pins on the board, right? You can configure the IO pins as input or output. You can decide whether you want to enable the analog pin or a digital pin, or you can decide whether you want the pin to be a UART based channel to transfer or receive data, or you just want it to be a normal IO pin, right? So all of that configuration goes into the setup function. So this setup function will just run will just run once, meaning it just sets up the pins in a particular configuration, and then you're all set. The board is set to a particular configuration, and then it is ready to run a particular task or a particular piece of code in a loop. So that's the first part, the initialization part of the board. Second part is the loop. This loop is basically the piece of code that will keep running on your Arduino system, right? So let's say that if you just want an LED to turn on and turn off continuously, you can just add two lines of code here to turn on and turn off the LED. We'll look at that, how to turn on or turn off an LED too. But you'll basically put that piece of the code here, which will keep running continuously. unless you hit the reset button on the board, or you prompt the board, or you remove the power source to the board, right? It will keep running continuously. So these are the two parts: the setup part and the loop. The setup part is initializing the board to the configuration that you wanted, and the next part is the loop part, which keeps running continuously. So with this bare bone structure, we'll now look at how one can start, configuring LEDs or the digital IO pins on the board. So there is this. This is a simple. So basically, all these examples here are available on the web editor. You can just go check any example here, and read the code and try to get a hang of it, like what it is trying to do. If you have a board at your home, you can just flash the code onto the board and see what it is doing. There's a good description of the code here at the top of the file. It tells what the code is basically doing, so you can read that and you can try to understand how the board is working. There are different examples. There's example about how you can use the IO pins, how you can calibrate the analog input that you're receiving. You can you can use it to drive. You can use the analog output to drive LEDs. You can have fading LED effect, meaning LED with a brighter output to a dimmer output, right? You can have those kind of applications here. So you can just go through these codes. That will give you a good sense of how all of the peripherals on the board is used. It also talks about the communication part of it, meaning you can use the board to communicate with other devices or the PC system that you have, right? It talks about the UART protocol, the MIDI protocol, the I2C protocol. There are different communication protocols, and there are examples provided here about how you can set up the board to communicate with another devices. Similarly, there are the sensor modules to control PWM generators, so you can look at that part of code. For now, for the sake of simplicity, I'll just look at this base. I'll start with this basic program, right? So as I mentioned before, this is the setup part. Setup part just initializes or configures the board the way you want it. For example, it is now configuring this LED bulletin. That is basically a pin on the board, the digital pin 13. Uh, if you remember, I mentioned that there is an LED which is connected to the digital pin 13. So this is what it's saying. This is the pin board, meaning you want the digital pin 13 to be an output pin. So you're saying that this is a defined this is a constant defined mentioned in somewhere in the libraries. This means the digital pin 13, and this pin mode function will configure the digital pin 13 to be an output pin. So you're setting up this pin as an output pin. So once you flash this program on your Arduino board, and once it starts running, it starts with the setup function. The setup function will configure this pin, and then it will jump onto the loop. The loop part is basically you are writing a digital output to this pin 13, right? Digital output just provides two options, right? It can be either high or low. It's basically one or zero, right? It's just a binary representation of it. So digital write pin 13 high means you would provide an output 1 on pin 13, and digital write pin 13 low means you'll provide an out 0 on that pin 13, right? And what you're doing is you're turning it high and low after 100 milliseconds. So this delay function takes in an input, and that input is basically the number of milliseconds for which you want to just spin and not do anything. So you turn on that pin 13, wait for 100 milliseconds, which is 1 second, and then turn it off, turn the pin 13 off, and then again wait for 1 second. Now this keeps happening continuously. So you're turning it on, waiting for 1 second, turning it off, again waiting for 1 second. And at the output of this pin 13 is a LED connected to it. So that LED will continuously turn on or turn off. So this is a very basic example of how you can start programming your Arduino board. And I would really suggest that start with very basic programs, so that will help build a very good understanding of the hardware and the software that you're designing for the system. Similarly, there are other examples too. For example, this is this button program, right? What you're doing is you're taking an input, you're taking an input and then providing that input to another pin. So you're taking an input from pin X and then you're providing the output to pin Y. And how are you taking an input? You're connecting a normal push button to this input pin. Uh, the pin number is specified here, which is basically pin 2. So you're making the pin 2 as an input pin, and you're making the pin 13 as an output pin. To the input pin, you have connected the push button. To the output pin, you have connected LED. So that's the setup part. So once again, when you flash the firmware on the Arduino board, the setup part will run. It will configure these pins, and then it will jump to the loop part. In the loop part, it does this continuously. So what it does is digital read, basically reading the input from button pin, which is pin 2. So it reads the input from pin 2, and digital read means it will either read 0 or 1. So it reads 0 or 1 from pin 2, and then it will check if uh, the button state is high, meaning if the input is high, then write it to the LED. That means turn on the LED. If it is not high, then turn off the LED, right? Basically writing high or low to the output pin, which is pin 13. So you take input on pin 2, uh, and based on the input, you make a decision and write it to the output pin, which is pin 13. So this is how an input output. Uh, this is how basically I/O works on the Arduino board. You configure it, and then you run a particular task in a loop. So for now, keeping I just have 5 to 10 minutes. I'm not going to go over all these programs, but you can take a look at the program. They are very simple. They just configure the pins and then run some part of the code continuously. And the good part of the web editor is you have these library functions like pin mode or digital read, digital write, which just abstracts all the hardware complexity and allows you to write a simple program which can then perform the task that you want. So so basically coming back to how one would start programming the Arduino board, right? You'll first select the board. You'll start with your sketchbook, write your own program. Once you're done writing your program, you'll hit this verify and save. What this verify and save will do is compile your program, check for any syntactical or major functional issues, and then it will generate a hex file in the background, right? So here it says that it was able to save my program and it was done verifying the blink copy I know. That's basically my program. So it saved it and it verified that my program is coded up correctly. And the next thing is, sorry, the next thing is you can then it generates the hex file in the background, right? So the next thing is you can just use this arrow button, which will just flash the program on the Arduino board. Right now I can't do that because I don't have the Arduino board connected to the system, but it is very simple. Once you once you connect the board and click on this arrow button, it will flash that executable file onto the Arduino board. So programming the Arduino board, there are just 3 simple steps. You select the board, write your program, and then flash it onto the system. Once you flash it onto the system, you just need to press the reset button, and then the entire board will function as per the code designed here. So coming back to my presentation, we discussed what the Arduino board is. So coming back to the agenda, we discussed what an embedded system is. I gave a brief intro about what the Arduino platform is. We looked at the Arduino board. We saw how one can start programming the Arduino board using the IDE, the offline tool, or the online web editor. The last is I just briefly want to talk about other embedded boards. So we looked at Arduino, which is one of the most popular ones. But is that the only option available? No, there are too many other options that you can use for your purpose. So there's Beagle board, Atmega base board, Raspberry Pi, Intel NUC, or NVIDIA Jetson. These are just few of the other popular ones, but there are just plethora of options available there. You can just select from all the options available which suits your purpose, right? And since you guys will be working on your second year, third year, or final year projects, most likely you'll need such embedded boards to design a system, a full-fledged system with hardware and software on it, right? So selecting a particular board is again very important. You can for sure go with the Arduino board. The Arduino company provides different flavors of the Arduino board itself. You can go to the website and read more about it. But you can also you should also go through the other options that you have, right? So basically, how would one select a board, right? These are the three basic steps that I can think of. First is a minimal system but serves the purpose. Again, if you think about the characteristics of an embedded board, the embedded board should be a minimalistic system, so it is bug free, it is crash free, or it does not hang, but it is able to serve the purpose of your application, right? It should not happen that the system is not capable of running the application that you want it to run. So it should be a minimalistic system, but again, it should also serve the purpose. The next is check for all the documentation available, meaning you would need to understand your hardware really well so that you can get the maximum out of it, right? So check for all the hardware documentation available for the system. Check if all the details about the components is available, how you can easily replace the components or how you can easily access the components. Um, yeah. For example, Arduino website provides a detailed data sheet of the Atmega baseboard 2 and the entire Arduino Uno board. So once you buy the board, you'll have access to all the documentation available on the website. The next is the software stack. So not just the documentation, but the software stack becomes extremely important too. It'll just save you a lot of time. For example, the Arduino IDE, the Arduino web editor tool or the offline tool, it makes the developer's life so simple that you can just use the library functions and configure the system the way you want and get started with it, right? So check that there is ample of software support for the system that you want to use. Another example is the Raspberry Pi board. If you go to the Raspberry Pi board's website, Raspberry Pi company's website, they have different operating systems available on there, which you can just download and flash it onto your system. They have all the drivers or the software kernels available on the website, so you can just download it with one click and install it on your system, right? So a good software stack support is really important, and check the developer community too. The developer community is basically any websites or blogs which are involved in these embedded board designs. They usually talk about which board is currently being used widely and which has all the support available, which is bug free and has a perfect hardware design too. So basically, keep these three things in mind. This will help you in your near future for your projects. Mainly, think of a minimalistic system that serves the purpose with good documentation and has continuous software stack support. Lastly, few sample projects. So I have, I mean, during my engineering and after, during my engineering projects and even in the industry, I have used Raspberry Pi boards and NVIDIA Jetson boards very often. The Raspberry Pi board is a microprocessor board, meaning it has an ARM processor on it, which is capable of driving servo motors, cameras, a lot of other external devices. It can run a Linux operating system. That means you can write heavy applications like image processing applications using OpenCV or some fancy libraries out there. So you can really develop a high performance embedded system with a Raspberry Pi board too. The next is NVIDIA Jetson. NVIDIA Jetson is a really powerful board in the sense that it has a really high performance for AI and ML applications. And since you know that now every embedded system is becoming more smarter and smarter and is consuming a lot of data, the NVIDIA Jetson board is extremely helpful in that case. It has high data performance, and also It is widely used in the field of robotics or vision based applications like autonomous robots or IoT devices or drones. NVIDIA Jetson is a really interesting platform. It has all the software support available. It has ample of documentation out there, so you can take a look at it too. Uh, but again, to start with something simple as an Arduino board. Understand how a microcontroller works. Understand the basics of how software programming works. Understand how software and hardware work together to form a system, and then go on to using the Raspberry Pi or NVIDIA Jetson system. Since these are more complicated and require much more knowledge than using an Arduino board. Uh, in my final year engineering project, we worked on adaptive traffic control system. So we used cameras, servo motors, lot of other peripherals, right? We had to use all those peripherals. But to prototype the concept, we started with an Atmega baseboard, which is just the Atmega microcontroller and some I/O pins. We started with that board. We wrote some simple program on it. We tried the I/O pins. We tried the peripherals. It worked perfectly fine. It gave us all the output that we required. Then we moved on to the Raspberry Pi board, which is the more complex system, and there we use the more intricate libraries like the OpenCV library or the IPP libraries for image processing. And we had a full-fledged embedded system which was able to capture images from the camera, process it, and then drive the servo motors or other peripherals connected to the Raspberry Pi system. So that's how I went ahead with my project with a simplistic design first, prototyping it, checking if the prototype works, and then moving on to a complex system like Raspberry Pi. So you can. My suggestion is to follow similar steps for your projects too. Um, yeah, I think that's all I have. So yeah, I think that's all about the presentation. I spoke about the what an embedded system is. We discussed what the Arduino platform is, and also looked at the other options available. I now want to give some time for Q&A. If anyone has any questions, feel free to shoot. I'll take them now.
We have a question in the chat box from Kunal.
Okay. Can you please read out the question? I can then answer it here.
Okay, he is asking for suggestions of any book or any resource for embedded systems and for learning Arduino editor IDE.
So for learning Arduino Editor IDE, I would suggest the Arduino website itself. They have a lot of information on there. So I'm assuming that since you want to know more about the system, you'll start with one embedded board, right? So I would suggest start with the Arduino Uno board. Once you buy the board and once you have made a profile on the Arduino website, you'll have access to all the documentation out there. So for the Arduino board, I would suggest going to the Arduino's website. And for general embedded systems, I would suggest you guys to start with learning what a microcontroller is or what a microprocessor is, because that's where the entire embedded system starts, right? So the other components are important, but the microcontroller microprocessor is the most important thing. So start with very basic microprocessors, understand how a 8085 or 8051 works, right? You guys might be having courses which will talk about these processors. So start understanding these processors. There are a lot of books out there. What I could do is after this session, I'll just provide references to the IETE committee, and they can then share with all of you guys. But there's just a lot of information. I would suggest start with very basic stuff like 8085 or 8051. Understand how do they work. There are really good books out there from amazing authors. Understand these processors and then move on to how do these processors start talking to other components on the board. Um, yeah, that's my suggestion. Are there any other questions?
Kunal has another question. He is asking that you said at Mega, in at Mega we use either Wi-Fi or Bluetooth for communication, and if there are any software or applications to secure this connection.
So to secure the connection, so from the security perspective, what can one do, right? You can, so if you want to transfer data, you can encode the data, you can encrypt it, you can sign the data and pass a signature along with it. So when on the receiving side, whenever they receive the data, they can decrypt the data or check if the signature of the data matches, right? You can hash the data. You can do a lot of things. But to do all these things, you need a processor or a controller which is capable of running these applications, right? So to even compute the signature of the data, you would need some computation power for the microcontrollers, right? So you don't need external software to do that. You can do it yourself too. You can just compute a basic hash of the data. Like you can just do some kind of parity hash or some kind of hash, and then pass the hash along with the data itself. And at the receiving end, someone can just decode the data using that hash or some kind of key, right? So there are softwares available, but on embedded systems, I would suggest try and use the minimalistic code. And if you use an external software, it will come with multiple layers in it, right? And that will just overburden the embedded system you have. So just try to find simple solutions to transfer your data across Bluetooth or Wi-Fi. But if you're using a full-fledged system like a Raspberry Pi, there are a lot of ways how you can secure your Bluetooth or Wi-Fi connection. So I don't want to quote any specific software because all of them are paid. You can just search for open source softwares for your design, for your prototype, and then if you think that you have a full-fledged idea which can work, you can then use the proprietary softwares. But yeah, start with something really basic. Start with a basic security protocol for your system. Encryption, encoding, signing, these things are basic. And there is ample of documentation available on these techniques too. Um, and you guys might be learning about it in your engineering too, how to encrypt or how to sign a data and then transfer your public and private key along with the data too. Does that answer your question, Kunal? Okay.
Yes, thank you.
Yeah. Are there any more questions?
Should we start with the Arduino or Raspberry Pi?
Oh, start with Arduino for sure. Raspberry Pi is much more complicated. You would need a Linux OS running on the Raspberry Pi board. And Arduino Uno board is really simple. So yeah, start with the Arduino Uno for sure.
Sure. And the career opportunities?
In the embedded systems field,
Yeah, in the embedded systems.
oh, there are a lot of career opportunities. You see so many startups in India these days working on some kind of embedded device, which you see fancy applications like a drone used in pre-wedding photography to applications like a embedded device going onto a satellite, right? The smaller satellites basically. So there are just too many opportunities, too many startups working in the field of embedded systems. So I think the more knowledge you have in the field, the better it is. Not just the startups, but even the bigger players like Intel, Nvidia, AMD, Qualcomm. These are always on the lookout. Google, Microsoft. They all are working on some kind of embedded system, some kind of embedded board which suits their purpose. For example, Nvidia is building this platform, and this platform is going into all the fancy cars. If you think of a Mercedes, it will in the future Mercedes car will have an Nvidia platform, Nvidia chip on it, which will have and the car will have cameras and lot many lidar sensors. The car will be an autonomous driving car, right? So it is again an embedded system, right? It is not a general purpose computer. It is an embedded system which has a task of capturing images and then making decisions for the car to drive, right? So there are just too many companies in and embedded systems is used in like every application, every industry. If you think of the oil industry, big players like Reliance Industries or ExxonMobil or British Petroleum, all of these use embedded systems or embedded devices in remote areas like the mining or refining sites where humans can't go, or it'll be harmful for humans to go, right? So they deploy these embed systems to capture data. So I would say that embed system is used in nearly every industry, and with the need for the devices or the applications, basically systems becoming smarter day by day, you would see the growth of this industry pretty fast.
Thank you, sir.
And I would suggest, if you guys are looking for internships and opportunities around in the industry, uh, I guess you guys should start with hands-on experience. Uh, yeah, you can read code and learn code too, but then hands-on experience is really invaluable. Usually, industry looks for the companies in the industry, they look for hands-on experience as much as possible. So pick up any board, try to study the board, try to develop some software on it, and understand how both the software and hardware work together. That's what basically an embedded system is, right? So try to get as much hands-on experience as possible, and I think that should see you through working in some good industry, some good company, or for some good application. Are there more questions?
Do you have any more questions?
Do you have any further questions?
I think we are done with the questions. I hand it over to Ritik.
Hello, I'm audible.
Yeah, you're audible now.
Is my voice echoing or not?
No, you're audible.
One second. Yeah, I will just.
In the meanwhile, I also want to mention this, that uh, if you guys want to talk more or know more about anything embedded systems, or if you want to discuss any ideas, or if you have any questions, feel free to reach out to me on LinkedIn. You can find me on the LinkedIn with my name. I'll just mention it here if it's already not there on the planet. I'll be happy to help out uh, with any further doubts or questions you may have.
So, good evening, everyone, to one and all present here. Thank you so much, Karan sir, for such a great webinar. It's such an honor for all of us sitting us here in this webinar for getting the opportunity to learn the fundamentals of Arduino and its alternatives, like you mentioned about NVIDIA and the other. So, on behalf of S.P.I.T, I would like to express my gratitude towards you, sir, to take out your time for from your busy schedule to grace this event. Would like to thank you, everyone present here, for joining, for being the part of this webinar, for a wonderful audience. Thank you, sir.
Thanks. Thanks, Ritik.
Thank you.
Thank you, guys. I'm going to sign off now.
Thank you,
Thank
sir.
you, sir.